So this is an exercise in working with a definition of cyclic group and the definition of generator, right? That if we can be careful enough with that, then this proof should fall out of the sky, more or less. That's one of the nice things about abstract algebra in comparison to, for example, real analysis. In abstract algebra, once you have the right definitions on the page, often the logic can kind of write itself in a lot of cases. But real analysis, you get all the definitions down, and there's probably still a lot of calculation to do. But that's, maybe my bias showing through a little bit. So the question here is, if G is a cyclic group and has generator A, and if there's another element of that group called H, and if H to the K equals A, so in other words, if there's some power of H which gives me the generator A of the group, then what do we say about H? If H can generate the generator, then what do we say about H? Is also, so that's the same conjecture that you all came up with. H is also a generator for the group. So there is a good hypothesis. So yeah, now the trick is proving it. Let's real quickly, I just want to look at an example. So let's suppose that I have a group that's finite and cyclic. Maybe I'll think of it as Z mod 12, just so that we can use a clock to organize our arithmetic here. So what's an example of an obvious generator for Z mod 12? We talked about obvious. Yeah, so one is an obvious example of a generator. So let's, for the moment, let's have that play the role of our A. Right? So obviously 1 is a generator, because if I add 1 to itself repeatedly, I get around every single hour on the clock back to the top of the clock, which we're going to call 0 instead of 12. Right? All right, so that plays the role of A. Now the question is, suppose that I have some other element on my clock that gives me 1 when I raise it to a certain power. And by power here, remember, this is an additive group, Z12. So power means add that element to itself repeatedly. So let's suppose that I say we take H equals 7. Okay. Then let's see what happens when I add 7 to itself. 7 plus 7 is 2, right? Exactly. 2 plus 7 is 9. 9 plus 7 is 4. 4 plus 7 is 11. 11 plus 7 is 6. 6 plus 7 is 1. And so we've arrived back to 1, right? Which is what we wanted. So that means that 7 to the power, this is mod 12. So 7 to the power 7 is equal to 1 in this example. So that's, and by power, I mean multiply, not take an exponent, right? Because it's the repeated operation of the group, plus 12. And by 1, I mean equivalent to 1 mod 12, right? So this is, take this arithmetic within the context. So this equation down here is playing the role of the observation H to the power K is equal to A. So that's what's going on here. Equals A. All right, so then my question is, how can we use that observation that it takes 7 H's to make an A, in this example? How do I then know that I can make every element of this group out of H's? For example, how do I get 4? How do I build 4 out of A's? How many A's do I need? 4. Yeah, A to the 4th gives me 4. Right? So A to the 4 power gives me 4. But I can make A out of 7 H's, right? 7 H's make an A, and 4 A's make 4. So how many H's will make 4? Let's plug it in, right? A is equal to H to the K. So if I plug in H to the K sitting right here.
Should be 11. Yeah.
Careful. So, right, 7 to the power 7 to the power 4. Yeah, so by properties of exponents, this is 28 copies of 7.
But can't you get rid of 24 of those?
If we wanted to.
Okay.
But we can decide whether that's necessary to our proof. So why does this for example, show me that 7 has a chance at being a generator for this group? Because we could write 4 as some power of 7. And that power is 28, but in particular, it's just an integer, right? And isn't that all that we need to know when it comes to expressing an element as a power of a generator? We just need to know that there exists some integer that makes that power of the generator equal to that element. So is there a clue to how we can structure this proof buried in this example? And before we write it formally, let's write it on the back of a napkin. So what's the principle here? Where did the key step happen?
When we replaced A with HK.
With h to the k. So that was where we transitioned from what we know about A's identity. A is a generator of this group. Right? And then we shifted into saying something about H, right, which we need to be able to conclude is a generator. Right? So if we sort of follow this back through, I picked 4 at random, right? I could have done this with any element of my group. So this 4 is just going to be my arbitrarily chosen G out of my group, right? So I choose G arbitrarily. And then I made the observation that since A was a generator, A raised to some power is going to equal G. So thus, G is equal to A to the, what do you want to call this power? N? Okay. For some integer n. Again, since this is on a napkin, I'm going to write some n integer right there, as opposed to quantifying it first. All right, so then that corresponds to this line. But then what happened on my next line? The magic happened. H to the k. Yeah. H to the k to the power n. And that's equal to h to the k times n. But then what does that tell me?
Because k and n
Mhm.
are integers.
Yeah.
And that when we multiply two integers, we get another integer.
Integers are closed under multiplication. Yeah.
So g is equal to h to the z.
G is equal to h to the power z for some integer z.
Covered up Hilbert Hotel.
I have covered up the Hilbert Hotel. Right. So in other words, since G was arbitrary, what do we get to conclude?
That H can generate all G within the group.
That H can generate all the elements within my group, right? This is what allows me to write down here at the bottom. I'm going to erase that right there. I can now write for all G in my group, G is equal to H to some power Z. And that was our burden of proof, right? If we want to prove that H is a generator, we need to show for all elements of the group G that there exists some integer, Z, such that G is equal to H to the power Z. And we just did that. That's our cocktail napkin version of this proof. And in the interest of time, I think we won't write out the formal structure of this. But that's an outline of the proof for this. Other